I said it like okay. All right. Let's go like this. That's good. Okay. All right. Greetings, scholars. Welcome, scholars. Let me see. As far as announcements, no major announcements other than, midterm grades are there. Only thing left that I need to kind of work on to update is my YouTube channel organization. Just as far as like, putting videos into the proper playlist and things. Most, if not all, the videos are there. I just need to like I was saying, like just organize them. So we're going to be continuing chapter 2. As usual, if you have questions, feel free to unmute yourself or type in the chat and we can talk about it. Otherwise, we're just going to kind of forge ahead. Is this playing properly? Okay, there it is. Okay. Yeah, so we're working on chapter 2, polynomial and rational functions. And so today we're going to start on section 2.2, polynomial functions. We'll get as far as we can together. And then on Wednesday, we'll see, if you guys want to keep doing the lecture on Wednesday, we can, or we can go through as many homework questions together as we can. But this is definitely one section where you want to see the whole presentation. So, it's definitely a good idea to use my pre-recorded lecture. All the stuff that's in the recording is the same stuff I would say as if we were live, right? And so if you watch the recording, just write down your questions, either email me or ask me at the next class, and then, that's kind of how we do that. Okay, so 2.2 on polynomial functions, a few objectives. 1, learn properties of the graphs of polynomial functions. 2, determine the end behavior of polynomial functions. 3, find the zeros of a polynomial function by factoring. Okay, factoring, right, okay. 4, identify the relationship between degrees, real zeros, and turning points. And 5, graph polynomial functions, okay? So a polynomial function of degree n is a function of this form where n is a non-negative integer and the coefficients an minus 1, all the way down to a naught, are real numbers where an is not equal to 0, an being our leading coefficient. So a polynomial is really just a finite sum of monomials. And a monomial is a one-term polynomial that's going to take on the form. You have some real coefficient times some variable raised to a non-negative integer power or exponent or whatever, right? So then the polynomial is just a finite sum of those. Again, we have some real coefficient times a variable raised to a non-negative integer exponent. And then the polynomial is just a finite sum of monomials, okay? So the term anx to the n is called the leading term. The number a sub n is called the leading coefficient, and a naught is the constant term. A constant function f of x equals a, where a is not equal to 0, which may be written as f of x equals a times x to the 0, is a polynomial of degree 0, right? So when we have f of x equals some number other than 0, we call that a constant function, like f of x equals 2, f of x equals 7, f of x equals 937 and 83. I don't know, I'm just trying to think of some random, right? But when you have f of x equals to a number, we call that a polynomial of degree 0 because it can be written as that number times x to the power of 0, right? But the zero function, f of x equal to 0, has no degree assigned to it. Yeah, I do not want to talk. Like I was like, all right, I gotta get something. Okay, I'll get something. We said that this has no degree because f of x equal to 0 can be written as 0, which also can be written as 0 times x squared, which also can be written as 0 times x to the 5, right? Because we can write that x to whatever power we want. It all collapses to 0. So then that's why we say that this function has no degree assigned to it. Polynomials of degree 3, 4, and 5 are called cubic, quartic, and quintic polynomials. So then this expression here that you see is a polynomial, and the function defined by f of x equal to that expression is what we call a polynomial function. And I'll check attendance again in just under 10 minutes for anybody that's coming late. And then this equation where you have the polynomial equal to 0 is called a polynomial equation. Okay. So the domain of a polynomial function is a set of all real numbers. Something's missing there. Let me back up. Okay, never mind. That's not. The graph of a polynomial function is a continuous curve, right? So here. So like notice we can pick any point on the graph and start tracing it. We can get to any other point without picking up our pencil, right? So all the points are connected with a smooth curve, no holes or gaps or breaks. And this graph on the other side, say we were to pick up any random point and then we start tracing, in order to get to these points on the other side, we have to pick our pencil up and then put it back down, right? So this is an example of something, a graph that has a hole or a gap or a break. So then this cannot be the graph of a polynomial function. Polynomial functions are continuous. So I just realized why I'm yawning. I made some spaghetti and like, I guess my nose is stopped up. So I couldn't taste properly. So I made the spaghetti extra spicy, but that's because I couldn't taste it. And so when I ate it, man, I was sweating like I stole something. I was sweating so much. And it tasted good, like from whatever I could taste, but I realized it's like, damn, I think I over seasoned it. So it's like extra spicy, but it tastes good. And it's my nose is stopped up. So, you know, that's what's getting through. But then that explains why I'm so sleepy, because I had like 2 bowls. It was so yummy. So I'm like, and I took a nap. I took like a 2-hour nap, but I'm just like, my body's like, nope, we got the itis. Like, so it's gonna be a long 3 hours for me, but that's okay. We forge ahead, right? The graph of a polynomial function is a smooth curve, right? So on the left, notice this graph is a smooth, continuous graph. There are no holes or gaps or breaks, no, you know, all the corners are smooth corners, right? But then the graph on the right, we have these sharp corners. You have a sharp corner here, sharp corner here, sharp corner here, right? Because of these sharp corners, this cannot be the graph of a polynomial function. Even though the graph on the right is continuous, there are no holes or gaps or breaks. But because we have that sharp edge, that means it cannot be the graph of a polynomial function. Okay. What time is it? So state which functions are polynomial functions. For each polynomial function, find its degree, the leading term, and the leading coefficient. So for A, right, we have the sum of 3 monomials, 5x to the 4 minus 2x plus 7. So then, yeah, that is a polynomial. Okay. This color so it pops a little bit. Can we move this? That's fine. So for A, we would say yes, a polynomial. I'm just going to abbreviate. The degree is going to be the highest power on any term. The highest power on any term here is 4. The leading term, I'm going to abbreviate as LT. That's going to be the term with the highest power. So that's going to be 5x to the 4. and the leading coefficient is the constant on the leading term. So in this case, it's going to be 5. So we got yes, it's a polynomial. We got the degree, the leading term, and the leading coefficient. So then for B, if we were to focus on this part here, we would say, oh yeah, it is a polynomial. But one property of polynomials is that the domain is all reals. This domain is restricted, so this is not the graph of a polynomial. So not a polynomial. B. Okay. And then g of x is not a polynomial because its domain is not all reals. So a function of this form is called a power function of degree n, where a is a non-zero real number and n is a positive integer. All right, we have f of x equals a times x to the power of n. We call that a power function, where a is a non-zero real number and n is a positive integer. So then if we consider a power function and say we let the power be even, say it's an even power, then if we replace x with negative x, all right, so if we have an even power and we say negative x to an even power, that's going to give us positive x to that even power, right? It's like if we said -1 quantity squared becomes +1. So this is it mimics that. So then when we evaluate f of negative x, we replace x with negative x and we simplify, we'll eventually get back to the original in this case, right? So f of negative x equal to f of x, that's the definition of a function being even. Functions that are even symmetric with respect to the y-axis. The graph y equals x to n where n is even is similar to the graph of y equals x squared, okay? So again, the definition of a function being even is when we replace x with negative x, we get back to the original, okay? So replacing x with negative x and returning to the original is the definition of a function being even. Then it stands to reason, okay, odd. Let's see what happens. So then if we consider this power function and let n be odd, if n is odd, then negative x quantity to the power of n. So if we have an odd number of negatives that's being multiplied, then it's going to be the same as a negative times x to the n. So then when we evaluate f of negative x and simplify, we get a negative times the original. So when we start with f of negative x and we finish with that. So a quick recap, a function being even, when we evaluate f of negative x, we get back to the original. A function being odd, when we evaluate f of negative x, we get a negative times the original. Okay. A function being odd is the same as origin symmetry. The best way I can kind of describe origin symmetry, if you have a graph that has origin symmetry, if you were to cut the graph along the x-axis, put your thumb on the origin, and rotate the top half 180 degrees, it's going to match the bottom half. With odd functions that have origin symmetry, whenever we have x comma y, we also have negative x comma negative y. So all the points are symmetric and equidistant around the origin. They're kind of like doing a dance around the origin. Whenever we have functions that are even, whenever we have x comma y, we also have negative x comma y, right? Even functions are symmetric about the y-axis. So the y-axis cuts it in half. If you cut it along the y-axis and fold the left half to the right, the two halves match up. So that kind of confirms whenever we have x comma y, we also have negative x comma y. So once you identify the type of symmetry that you have, you can use that symmetry to generate additional points when graphing. Okay. All right. So we have these. We're going to explore this concept called n-graph behavior, and this is kind of piggybacking off of even functions having y-axis symmetry and odd functions having origin symmetry. Well, not really. It does align with that, but it's still its own thing, right? You see my time. Right on the money. Okay. Let me just check real quick before I go to that next concept. I think who's ever going to come is here for the most part. These guys is absent. Pretty good. That's looking pretty good. I only have 5 absent. Okay. So let's see. Oh, we gotta go with this. Okay. So in behavior of a polynomial function, we need something else. In this case, I think where n is even. Okay. So I'm adding this part in vocal. So in this first case, our a, which is our leading coefficient, is positive, and the degree of our polynomial is even. Not to be confused with even and odd function, like we said, we kind of discussed a moment ago. This n is referring to the degree of the polynomial, right? Or the power function in this case. So if we have a positive leading coefficient, because a is positive, that tells us the right-hand side goes up to the right. Because n is even, the left-hand side does the exact same. This doesn't give us any information about the middle, but we know that it goes up to the right and up to the left. Okay. So again, the leading coefficient tells us about the right hand. The degree of the polynomial, in even or odd, tells us about the left hand, right? Okay. So if we have a positive leading coefficient and it goes up, then it's safe to assume if we have a negative leading coefficient, what happens? It should do what? Fall to the right. So if our a is negative, it should fall to the right. And if n is even, the left does the exact same. For me, even means exact same, right? A negative leading coefficient falls to the right. And if n is even, the left hand does the exact same. So it falls to the left. Okay. So then now we saw 2 cases where the degree of our polynomial is even, and basically both ends went off in the same direction. Okay. So then let's see what happens when n is odd. Okay. So suppose we had a positive leading coefficient and n is odd. A positive leading coefficient means what? It goes up to the right. If the degree of the polynomial is odd, then the other side does the opposite. If even means exact same, odd means opposite in this context. So a positive leading coefficient, goes up to the right, and if it's an odd degree polynomial, it's the other side's going to do the opposite, so it's going to go down to the left. Right? We see it here. And again, this is our n is odd. So a positive leading coefficient goes up to the right, n being odd, the other side does the opposite, it goes down to the left. And then lastly, if our leading coefficient is negative, that means it's going to fall to the right. And if n is odd, the other side does the opposite, it's going to go up to the left. Right? So those are our 4 cases. Right? A negative leading coefficient falls to the right. If n is odd, the other side does the opposite, goes up to the left. Okay. Okay. So hopefully we're all aboard and not all bored. Again, if anything is not clear, feel free to unmute yourself or type in the chat to get my attention and we can talk about it. Otherwise, we're gonna press on. Forge ahead. So given this polynomial of degree 3, we want to show that this polynomial is approximately equal to the power function 2x cubed when the absolute value of x is very large. Okay. So I'm trying to get some colors that I don't normally have, like, yeah, like that color. I can't think of others, but I knew I was missing that one, so I'm gonna let that be for now. Okay, so we saw the 4 cases for the power function. The leading coefficient tells us about the right-hand behavior. The degree of the polynomial tells us about how the other end behaves. This doesn't give us any information about the middle. It just tells us what happens in the long term going to the right and what happens in the long term going to the left, right? Okay. I just felt like I had an Abbott and Costello moment just now. Who's on first? Yes is on first. No, who? That's what I'm trying to ask you. You know, like it's a player on first whose name is who, and they go back and forth like that for a while. Anyway, okay, so let's show how this polynomial is approximately equal to the power function 2x cubed when the absolute value of x is very large. So if we start with our polynomial, 2x cubed plus 5x, let me clean that plus up. Plus 5x squared minus 7x plus 11. Let me just okay, so then let's factor out x cubed from all terms. So if we factor out x cubed, then we're going to be left 2 plus 5 over x minus 7 over x squared plus 11 over x cubed. Oh, that's a good one. Share. Okay. So what did I do? Okay, that's fine. Oh no. Oh, I didn't know I was gonna do that. No. But then I didn't realize that those were linked like that. That's not fair. Okay, now I want to edit. You're not gonna let me edit here? I don't know how to change it back. Oh, there it is. What did I do? Okay, maybe I double clicked it. Okay. Can I add one? Now, if I could just add some, that would be nice. That's all I'm trying to do. Sorry, hang on, guys. Settings. Done. Yeah, because those are linked. That sucks. Okay. Okay. So then, if we consider these as the absolute value of x gets really large, like think about it. If we think about the 5, right? Just to yourself, you know, if you did 5 divided by 1, you get a result, right? If you did 5 divided by 2, you get an answer. If you did 5 divided by 5, all right, you get an answer. 5 divided by 10, 5 divided by 20, 5 divided by 100, 5 divided by 1,000, 5 divided by 10,000, right? So what do you notice as that base or as that denominator is getting larger and larger and larger, this term is getting closer and closer and closer to, so as absolute value of x gets large, this term tends to 0. Same thing for this guy and this guy, right? So as the absolute value of x gets really large, and I'll say, as the absolute value of x tends towards infinity, those guys tend to 0. So then this is approximately equal to, so the only thing that's going to be left is the 2 and the x to the 3. So it's approximately equal to 2x to the power. Okay. So we showed that p of x is approximately equal to the power function. So then, and we just saw a moment ago where, because the leading coefficient is positive, it should go up to the right. And because the degree of the polynomial is odd, the other side does the opposite. So it should go down to the left, right? So we know how this long-term behavior, we know how this function behaves long-term. And that means that this guy is going to behave long-term in a similar fashion. Okay. So we can use those 4 cases that we just discussed on the power function and extend them to polynomial functions. Okay. So given a polynomial function where the leading coefficient is not 0, then the leading term an x to the n, its leading term is an x to the n. The behavior of the graph of f as x tends to infinity or negative infinity is similar to one of the following 4 graphs, and it's described as shown in each case. The middle portion of each graph indicated by the dashed line is not determined by this test, okay? And basically this parallels what we said before with those 4 cases with the power function. Okay, so again here, this is where n is even, so the degree of the polynomial is even. Right. So a positive leading coefficient goes up to the right. If it's an even degree polynomial, then the other side does the exact same. So up to the right, up to the left. Again, the next case is if n is even, but our leading coefficient is negative, a negative leading coefficient falls to the right, and then an even degree, the other side does the exact same, so we're going to fall to the left. So falls to the right and to the left. Okay. Leading coefficient is positive, but now our n is odd. Okay. So up to the right, other side does the opposite. So it's going to go down to the left, up to the right and down to the left. And then the last case is where our leading coefficient is negative and n is odd. So it should go down to the right and up to the left. Again, this has no bearing on what happens in the middle. We're just this just gives us information about the long-term behavior of the graph. Okay. So yeah, with these concepts, I feel like the concepts are not difficult, but they can definitely be information overload. So it's like it's a lot of information in a little time. And also keep in mind that the things that we cover with this structure is only a quarter of what we covered in the past. Like if we did all the concepts, it would be 4 times the amount of information. We would have to do anywhere from 2 to 4 sections a week. So those students were like extra stressed out, right? So I think we've talked about this where, the faculty acknowledged how challenging college algebra was for students. And it's not just at Morehouse. This was like at least nationwide and possibly worldwide. Like college algebra was just whooping everybody's butt, like across the board. So Morehouse decided to cut the information in half and try to just pull out the pertinent, relevant information, because it's a lot of concepts and techniques in college algebra. Like one that we don't discuss, you don't really need them, but if you know them, it helps. But then, with the amount of information, it definitely became information overload, and it infringed on the law of diminishing returns. So they decided to invoke the energy of like less is more, provide less information, and that way you guys can retain more of it. So they cut the information in half and then broke up the remaining information up into 2 semesters. Right. So It was only one semester in the past, but there's a lot of stuff, a lot of different techniques, and we get into some of it, but there's a lot that's not there. But again, you can move forward without knowing that stuff and be fine. I didn't learn a lot of these concepts and techniques until I started teaching, because I started off in calculus and I could do the math. But I wasn't aware of like a function being even or odd. I didn't know that until I got here. Until I started teaching, I was like, oh, that's what because I had a grad professor that was talking about it. I was like, what is he talking about? And because I kept getting it wrong, I was like, huh? Then if I had known this, it would have helped me, but that's okay. Okay. All right, so let's see. Yeah. So use the leading term test to determine the end behavior of this graph, okay? So if we want to use a leading term test, all we need to do is focus on the leading term. Notice that our leading coefficient is -2, so that means our graph falls to the right, and it's an odd degree polynomial, so the other side does the opposite, so it should rise to the left. So I usually abbreviate it like this. It falls to the right and rises to the left. This doesn't give us any information what happens in the middle, but we know as x goes to positive infinity, y tends to negative infinity. As x tends to negative infinity, y tends to positive infinity. We're going to hang out for almost right at about 10 more minutes, give or take. Okay, these just didn't print properly, so I'm going to rewrite them so that they are showing properly. This one is supposed to say y tends, those r's are basically arrows. So y tends to infinity as x tends to negative infinity, and y tends to negative infinity as x tends to positive infinity, right? So that's what we just said with that abbreviated symbol that I put. Okay. So then real zeros are polynomial functions. If f is a polynomial function and c is a real number, then the following statements are equivalent. C is a zero of f. C is a solution or root of the equation f of x equal to 0. C is an x-intercept of the graph of f, and the point c, 0 is on the graph. So these three statements can be used interchangeably. So whenever we say x-intercept, that's the same as saying the solution of the equation f of x equal to 0, the solution or root. But that's the same as saying the zero of the function, right? So all three of these phrases can be used interchangeably. So we're asked to find the zeros of each polynomial. We'll do at least the first one. We might go ahead and do the second one. Maybe, maybe not. But I'll at least do the first one. Okay. And actually, what page is this? 30? Are you going to throw a tantrum? Oh my goodness. Thank you. Can we just copy here? Copy. Let me see how quickly. Let me give it a couple of clicks. Okay. I'm going to select 30, duplicate. That's exactly what I want. Cool. I hit done. Start here. Okay, cool. Okay. So for part A, we have f of x equals x to the power 4 minus 2x cubed minus 3x squared. And we want to find the zeros. So we're going to set this equal to 0, but what we want to do is factor. All right. So first thing is factoring. Now, if you're feeling uneasy about factoring, I would encourage you to check out my box link, like near the same location where I put the notes each day. There's going to be a folder that says called handouts. In that folder that says handouts, you're going to find two documents that can assist with factoring. One document is a summary of all the different factoring techniques, and it basically summarizes how to approach a factoring problem. All right. First, you ask, is there a greatest common factor? Then usually you have 1 or 3 cases. Then within those 3 cases, we have a couple of different techniques, and so on and so forth. And then the other document is going to be a scan of an entire chapter devoted to factoring. I pulled it from an intermediate algebra book I was working in once, and it basically provides practice, and it kind of goes through and walks through pretty much all the factoring scenarios, just like at least 90% of the factoring scenarios that we're going to talk about here together. So that's in our box folder and the handout folder. If you just want some practice on factoring, it's there. Okay, so here, first question we ask ourselves: is there a greatest common factor? Is there a greatest common factor? Yeah, they all have x squared, so we can factor out x squared from each term, and we're going to be left with x squared minus 2x minus 3 equals 0. Okay, so then we ask ourselves, well, this trinomial, can we factor this trinomial further? Okay, so we want to see, can we factor it into a form like this, where we have an x and an x? Because the second sign is negative, I know my two signs are opposite. One has to be positive and one has to be negative. Because the first sign is negative, I know my larger number is negative. So I'm looking for two numbers that multiply to give me -3, add to give me -2 is going to be -3 and 1. Okay. So then here we use the zero factor property. When two or more things multiply to give us 0, we set each factor to 0 and solve. So we have x squared equals 0, or x plus 1 equals 0, or x minus 3 equals 0. And if we solve each of these equations, we get x equals 0, or x equals -1, or x equals 3. So these three are the zeros of this polynomial. Okay, I'm going to go ahead and work B, and then when we finish B, that'll be it. 0, -1, and 3, and we should plug it back into the original to check. I'm just going to move forward. So let's work on B. So we're starting with g of x equal to x cubed minus 2x squared plus x minus 2. We're going to set this equal to 0. So in this case, well, first we ask ourselves, is there a greatest common factor? No, there's not a factor that's common to all. So the next question is, well, how many terms? Do we have 2 terms, 3 terms, 4 or more terms? So we have 4 terms here. So I'm going to use a technique that's called factor by grouping, right? So first, I'm going to try grouping the first 2 terms together, and let's kind of see what happens. So if I focus on the first 2, I can factor out what? X squared. So we can factor out x squared, and it looks like we're going to be left with x minus 2. Okay. So the hint is we're really looking for another x minus 2 on the right-hand side, and it's already there, right? So we just happen to already have the x minus 2 on this side. So then that blue thing is what we call a common binomial factor. So we can factor out x minus 2 from both terms, from those 2 remaining terms. So then if we factor out the x minus 2, then we're going to be left with, it looks like, what, x squared. Now this plus 1 can be difficult. You know, students tend to miss that. We can't factor sum of squares. If it was difference of squares, we can go further, but there's no special factor for sum of squares. So then if we use the zero factor property, set each one to 0 and solve, x minus 2 equal to 0. So then x equals 2. Now let's see what happens with this. We got x squared plus 1 equal to 0, right? This is a U-shaped curve that's been moved up by 1, so it lies entirely above the x-axis, right? So it never crosses. If we subtract 1 from both sides, we're going to have x squared equals to -1. Not a real solution, because when we're going to take the square root, we can't take the square root of negatives, so no solution there. Right? So then we only have 1, 0, which is x equals to 2. Okay. 0, -1, and 3. I think that's what we got for the first one, and we only got 2 here. Let me see what's on the next one. Okay. All right. So you definitely, I'm going to leave the rest as an exercise for you. You definitely want to take advantage of my pre-recorded lecture. Are there any burning questions before we go our separate ways? Going once, going twice. Okay. All right, gentlemen. So if there aren't any burning questions, we're actually going to go ahead and end the session here. From one beautiful mind to another, enjoy the rest of your day. We're going to meet again on Wednesday, same time, same place for the next installment. Take care, gentlemen. Peace.
Professor?
Yes.
I actually have a question right quick. It's just about the midterm grade and everything. Since I just got access this weekend, I just completed all the work that was past due, and I was just wondering if you can just update my grades just so I could see what my standing is right now, because I have to do a midterm report for my counselor, and so I was just trying to see if I could get that up-to-date grade on that report.
Let me think about it.
Yes, sir.
Okay, I need you to send me an email.
Okay. Yeah. Okay. Yes, sir.
It again and just try to follow with me like next class.
Next class. Okay.
Yeah. Just follow. If I haven't done it by next class, just remind me. And just kind of each class keep reminding me. It shouldn't take that long, but I just send me an email now and then just keep following up like until I do it.
Yes, sir. Okay, I'll send the first email right now for you. Thank you. No, you have a good one.
Professor Phifer.
Yes.
Yeah. Where do you put all the slides that we work on again?
Okay, so let me see if I can pull it up. If we go, I will do. So if we log into our Blackboard page, right? We go to Blackboard. When we open up our course, this is the 2 p.m. This is you all here, I think. I mean, your names were there, so I know I did that right. So then here, this is the landing page. We open up this main folder. And then, so right there, item number 2, you click on that and it's going to redirect you to Box. And it's all there in item number 2.
All right, thank you.
Any other questions going once, going twice? Forever hold your P's and race. All right, gentlemen, enjoy the rest of your day. Take care. Peace. $240.